So this is the fifth question of CodeChef Starter 119, Division 4, K odd sum. Okay. In this question, you are basically given two integers n and k, and we need to construct a permutation p, so p1, p2 till pn, and a permutation basically consists of all the numbers from 1 to n exactly once, and we need to construct this permutation in such a order that there are exactly k indices where I is from the range 1 to less than n, where p of I plus p of I plus 1, p of I plus p of I plus 1 is an odd number. Okay. Basically, after constructing the permutation, there should be at least k different places where not at least, exactly k different places where the adjacent elements sum up to an odd number. Okay. And it's also mentioned that it can be proven that under the constraints, there will always exist a solution. Okay. And yeah, let's see what are the constraints here. We have basically test cases up to 10 power 3. The n value can be up to 10 power 5, and the k value is mentioned to be in the range 1 to n minus 1. Now, notice that the k value can never be more than n minus 1 because sum of adjacent values, the number of sum of adjacent values will always be equal to n minus 1 only, right? They will never exceed n minus 1, right? So basically, if you have three numbers, there will be two pairs of adjacents, basically, right? So yeah, if you look at the sample cases, we have n value 4 and k value 2 here. Okay, so basically, we need to form a permutation for numbers from 1 to 4 in such a way that there are only two places where the adjacent numbers sum up to an odd number. Okay, so here the permutation is 4, 3, 1, 2. So 4 and 3 will add up to 7, which is odd. 1 and 2 will add up to 3, which is also odd. And 3 and 1 will not add up to an odd number. So basically, the criteria for only two adjacent pairs to be odd is satisfied, which is 4 and 3 and 1 and 2. These are the two pairs. Okay. And since we can have multiple answers, it's not necessary we have to print this. Any other possibility is also fine, right? So yeah, let's see how we can solve this question. So yeah, now in this question, since we need to ensure that there are only exactly k places where sum of adjacent elements equals to an odd number, let's first understand in what combinations do we get odd number as a sum, right? So if we have even plus even, what will that result in? It will result in an even number. If we have odd plus odd, that will result in an odd number. Only when we have odd plus even, okay, this is even, I'm sorry. Odd plus odd will result in an even. So only in the case where we have odd plus even, we'll get an odd, or if we have even plus odd, we'll get an odd. Okay. So only these conditions are required for us, right? Basically, we just need k different adjacent pairs where either of these conditions satisfy, right? Now, based on this, I can make another observation, right? So let's say given any n value, let's say n equals to 7, okay? Let's not worry about the k for now. If n is given as 7, and if I just simply arrange the numbers in sequential order, okay, 4, 5, 6, 7, okay. Now what I observe here is, since odd and even are always alternating here, right? Basically, one is odd, two is even, then again odd, even, odd, even, odd, even. At every single point, these two conditions are being satisfied. Either of these two are being satisfied, right? Here, even plus odd is being satisfied. Here, odd plus even, then again, odd plus even plus odd, and so on, right? So in this, we basically get how many pairs? We get 1, 2, 3, 4, 5, and 6. We get 6 different pairs where, or we can say 6 different indices where these conditions are being satisfied, right? That's true. Now, what is being asked in the question? In the question, it's been asked that we need to make sure only k different places these conditions are satisfied, not more than k, not less than k, right? So one way to solve this question is we can use some form of greedy or constructive algorithm. What we can do is, let's say, let me try some approaches. Okay, here, let's take some bigger test case. Okay, to understand how we solve this question. Okay, so let's take n value as 12 and k value as 7. Okay, now I need 7 different places where these conditions satisfy. Okay, so let me just do one simple thing. I'll just say 1, 2, 3, 4, 4, 5, 6, 7, 8. Okay, I'll arrange the first 8 numbers in an order as it is. I'll get 7 different. If I put 8 numbers, I get 7 different places where these conditions satisfy. Right now, after doing this, I just want to make sure that after this point, all the other places, the conditions don't satisfy at all. Right. Right. So how can I achieve that? What now after 8, if I want at all the places for the condition not to satisfy, for 8, I need to choose an adjacent number that is also even. So I'll pick up 10. After that, I'll pick up 12. Okay. Now I'm still left with 11 and 9, right? Now, if I try to put 11 and 9 here, there'll be another pair of odd and even, right? So now we have already picked up 7 here, and this will make it another 8th adjacent pair where odd and even are coming close to each other, right? But that's not what we need, right? We need only 7. Okay. So what can we do in this case? Now, if we observe here, at any point we stop, we can basically put all the remaining even numbers and all the remaining odd numbers just one after the other, right? And we'll get only exactly one place where this condition will be satisfied, right? Odd and even and odd, right? So what we can do is, instead of picking up 7, we pick up one less. Okay, so we can pick up 6 different adjacent indices. So for picking up 6 different, we basically choose 7 numbers, right? So instead of putting 1 to 8, we'll put 1 to 7. 1, 2, 3, 4, 5, 6, and 7, right? So this will make sure I have 6 different places where that condition is being satisfied, right? Now, after 7, I'll put an odd sequence. So, okay, whatever this number is, it has to, the next immediate number should be uh, basically an odd as well. If this is odd, this has to be odd. If this is even, this has to be, just like that. Okay. After 7, 9, and we have 11, and then we'll go back to 8, 10, and 12. Okay. So this is the odd part and this is the even part. There's exactly 1 between them, which will add another one. So 6 plus 1 becomes 7 total pairs, right? So this is just a simple algorithmic approach we can apply here. Okay. Now, if the k value was, let's say, an even number, okay. So let's draw that out. If n equals to 12, and if k was an even value, in that case, we can do the same thing, right? 1, 2, 3, 4, 5, 6, right? We get 5 different pairs here, right? And now here we continued from an odd sequence because the last number was odd. But here we'll do the opposite. We'll continue from an even sequence. So 8, 10, 12, and then we go to 9, 11, right? Okay, not 9, 11. 7, 9, 11. Okay, right? And we have 1 extra here. So 5 plus 1 becomes total 6, right? So this is how we solve the question. Simple logic, just go from run one for loop that goes from 1 till k, print all the numbers, and then go from k plus 1 till go from k plus 1 till n by incrementing 2 every single time, and then go from k plus 2 till n by incrementing 2 every single time. Okay, this is just very simple approach, right? So why am I choosing k plus 1 in this case is because um okay, we have to choose k plus 2 here. Okay, not k plus 1, k plus 2. Okay, so since after 7 we start from 9, we start from k plus 2 and go till n and pick up 2 every single time. So here is basically 9, 11, right? And then from k plus 1 we go till n by picking 2 every single time. So k plus 1 is 8 here, 8, 10, 12 basically, right? Same thing happens here as well, right? This is basically like a short instruction of how to approach the question. Okay, right? And since at the end we'll be just making in total of n iterations only, we can say that the time complexity will be O of n. Okay, and the space complexity will be O of 1. Okay, we don't need to store anything. We just need to store n and k values and run these 3 instruction loops. Okay, that's all, and the question will be solved.